the kind words. The clicker is...
And it's right here. It's
okay.
at the bottom.
Well, I want to also welcome everybody here. I want to extend our thanks and appreciation for you to take the time to come to this workshop. At the end of my slide, I want to expose you to another purpose that you're here. I'll wait till then to let you know what that is, but we have ulterior motives. The doors will shut in a few minutes and we'll have you captured. I would like to just recognize what I want to talk about right now is primarily just promotion of Landsat and convince you, if you're not convinced already, why Landsat is really the nearly perfect satellite for mapping evapotranspiration at the field scale, which is just one application for evapotranspiration, but it's a very important application when it comes to irrigated agriculture because it's on the field level that water rights are generally tied to, and we have to manage these property rights, the consumption, on a field-by-field basis generally, and only Landsat can bring us that resolution. I'd like to just recognize a lot of our collaborators through the years that have been working with us for the last 12, 13 years now on satellite-based remote sensing of ET. Why ET is important at the field scale, like I said, it varies widely from field to field, planting dates and what have you. Historical consumption is often important for water rights. We need to prove historical use. Sometimes the transfer has to be based on historical use. So the Landsat archive, the fact that it goes back to 1984 for thermal data is of immense value to show now a nearly 26, 27-year record of water consumption. Marketing, of course, you have difficulty marketing if you don't know what you can quantify. And a discussion we had yesterday with Idaho's congressional delegation made it very clear that water marketing is going to be opened up so much more widely and broader with consumptive use information. No longer do we have to argue about impacts and the quantity of impact as water moves around if we know how much water is going to be moving around. It clears the field. It's going to accentuate water moving from, hopefully from less valuable uses to higher valuable uses. So there's a definite economic benefit of being able to map ET at the field scale. And I think as a community, we need to make that much more clear to Congress. Why is ET mapping and irrigation important? Reasons we've talked about, but the U.S. has got over 50 million acres of irrigated lands. It's probably accounts for 80% of the water consumed, not diverted, but consumed. And I just want to say that if you're going to manage this very valuable resource that's worth some $200 billion, we figure, for just the value of the water rights, you better have some serious estimates of ET. And you better not, one value does not any longer apply to all. We don't use one ET value for corn for South Idaho. Those days are gone. Now we're looking at field-to-field variation in ET, documented historical use. We want that kind of information for the future. The state-to-state agreements are going to require it. And then within state, water rights operations is going to require it. Some of our best hydrologic models are going to require this spatial information on actual ET. Why use energy balance and thermal? Well, here's a whole list of reasons why actual ET might be something less than potential ET. And the thermal, as I'll show, gives us a very nice signal that's indicative of how much these things might factor into that. And of course, there's other stuff going on that we like to figure out from satellite. We like to use the energy balance for actual ET primarily because, again, actual ET isn't always the same as potential ET. For the same amounts of vegetation cover, you can have different amounts of ET depending upon the water availability primarily. So we look at what we can see from satellite, which is You know, the things that are connected to thermal, sensible heat flux to the air is largely a thermal convective process, has some aerodynamic wind aspects. Net radiation is a solar and thermally dominated process. Conductance to the soil is thermally dominated. So if we make our best estimates of what those are, and we assume then that the energy not explained must have been used to convert liquid water to vapor. That's the whole basis of this approach. Fortunately, it takes a lot of energy to evaporate water, and so, oops, sorry, went backwards. So we can make some pretty robust estimates. This is just a picture. Some of you have seen this before, just showing the large amount of variation in surface temperature we can see. This is South Idaho turned on its side looking west. Here's Twin Falls. Here's the irrigated areas, about 1 million acres. And here's the desert. You can appreciate that the desert's halfway at 11 o'clock in the morning when Landsat comes over. It's halfway to boiling, 50 degrees Celsius. The irrigated area, the evaporative cooling is pronounced, 20-degree cooling effect on the well-watered areas. And so that's the signal that we use. I'm just showing, these are some results from the metric process where oh, sorry, what did I do? We express the evapotranspiration as a fraction of reference ET, where reference ET, especially if we use an alpha-alpha reference, represents pretty much the maximum upper bound of evapotranspiration to expect based on energy availability. We use the Pima-Monteith standardized by ASCE to represent that upper bound, and then we scale to that. We do that to really anchor our calibration process. Rather than try to do everything from the satellite, we use the information that we are very confident in, which is the fraction of reference ET. What I want to point out here, though, is that there's a strong linear relationship between surface temperature, in this case delapse, because of course as you change elevation you're going to cool the air mass. So if we kind of inverse that process and take the lapse effect out of it, then we see a very clear relationship between surface temperature and reference ET on the right image, especially for desert, for agriculture, a lot of different conditions. I do want to point out, though, that this relationship is not always linear, which is why a person can get into some inaccuracy by just scaling ET using a linear function of temperature. In the case on the left, it's the same area, except it's a condition where there's only moderate wind, and therefore some of the convective buoyancy effects, which are quite nonlinear, start to play a substantial role in heat transfer, and therefore they impact the evapotranspiration estimation. So that's a reason that for the serious applications that are going to be required in water rights management, hydrologic studies, groundwater model calibration, we feel that a full energy balance is essential. You guys remember the movie Clockwork Orange back in the 70s, where they took this delinquent and they pinned his eyes open for about 24 hours, and they showed all these horror, violent things on the movie screen until he was so nauseated by it, he became a perfect human after that. How many saw Clockwork Orange? Hey, sweet movie, huh? Anyway, I'm going to do this to you. I'm going to show you ad nauseam field scale ET until you're convinced that you got to have Landsat. I mean, the advantage of Landsat for field scale is so obvious, and it's something that we as a community, as you heard Jim Irons say, Tom Loveland say, Tony Willardson say, Dave Tudhill say, we as a community have got to be more outspoken and more communicative about Landsat. That's our satellite. It's primarily our satellite to be used for evapotranspiration mapping. Anyway, here's some fields in South Idaho. We can see field-to-field variation. We can see within-field variation. If we had a sequence, we could see time variation. We can see all the behavior of water consumption, which is so meaningful to us because now we can, besides understanding it, we can even populate all of our water balance models or hydrologic models with much better data. We can understand yield differences. We can attempt to explain those There's so much we can do. Closer up, see in-field variation. Now some of this is probably just artifacts of, looking down 700 kilometers from space, but it's one of those things, to quote Bryce Contra, who's here, that if you believe it, then you can see it. Here's another one. We can even see texture in the, this is Idaho, so, if you don't irrigate, you don't have much, about 10 inches, 8 to 10 inches of rainfall, natural. So, but we can even see some texture out in the desert. And again, it's one of those things, if you believe it, you see it, this texture. But that's pretty meaningful even to a natural resources manager looking at sagebrush habitat. What is this texture of ET and vegetation health, fire potential in desert areas? So there's a lot of value that we can provide with these ET images. All right, that's enough. But anyway, I think you can appreciate, we can see individual fields, and it's just so valuable. I can't say that often enough. Now, some are quick to say, well, if you guys run out of Landsat, why don't you just start using MODIS? Well, this is the Bell Rapids Irrigation District. It's about 30,000 acres in south central Idaho. On the left is a Landsat image overlain by water rights polygons managed by the Idaho Department of Water Resources. Each of them have, well, this is a district, but corporately, those have to be aggregated to determine the historical consumption of Bell Rapids. Over on the right is a 1,000-meter thermal pixel of MODIS overlaid, the same ET information, but you can see we've got bleeding outside of boundaries. So, all the ET from this polygon is bleeding outside. So we're losing ET from inside the field. We're going to generally underestimate ET if we're surrounded by an area of having less than ET. So MODIS just can't do it for us, unfortunately, by itself. Now, if we go to the shortwave bands of MODIS, two of the bands that are used in this vegetation index NDVI are 250 meters. That gets better, but we start to lose information because we no longer have that thermal signal to tell us something about actual ET. Now we can only work on estimates of potential ET, and we're going to not have information on impacts of wetting events like precipitation. We won't see that with the vegetation index. Bell Rapids is a nice example because here Bell Rapids is in year 2006, 1 year after the state of Idaho purchased the water rights to use in salmon recovery efforts. And we can still see a little bit of trace there in the circle. And over on the right is what we just looked at. That was a few years before, and now here it is without water. So we can actually document with a thermal satellite what residual ET is. And this is pretty important in places like California where we are rotating fallowing, taking water to the cities. Well, if you fallow a irrigated parcel, the ET doesn't drop to zero during that fallow year. There's a residual ET because of stored moisture in the soil, rainfall, weeds growing. It's important to know what that residual is so that we only harvest off the part that really is not consumed. We can make estimates of ET from vegetation index. Apologize that these are all green color, but in the lower left here is a surface temperature map. The darker the green, the colder the temperature. Over on the right is vegetation index. Darker the green, the higher the vegetation. And so you can see on the upper right is an ET estimate just based on taking 1.25 times the NDVI. And so, of course, it corresponds perfectly with the NDVI. Over on the left is ET coming from the energy balance. You can see close correspondence, but you can also see some fields that show residual evaporation from wetness with the energy balance, and the vegetation says there's nothing happening there. So it is important, I think, to have that thermal imager, and we just can't thank NASA and USGS enough that is on Landsat 8. Another important thing that is a nice outcome, especially something we do in metric, we calibrate to that reference ET. One of the benefits of that is it does make it congruent with the crop coefficient method. And this is an overlay here of these, these are satellite Landsat overpass days, and so this is kind of a crop coefficient curve, if you will, and then we're comparing it to some of our traditional methods we see very good correspondence, which is very comforting to Department of Water Resources, who has to shift from different types of information sources. We just can't use other satellites because of the coarseness usually, or some of the European satellites, there's no thermal band. Some of the work that's being done, and here's some work that we're doing at Kimberly. We are taking that 1,000-meter thermal pixel from Landsat over on the left. We're coupling it with some vegetation index at 30 meters with Landsat, and then we're producing a sharpened thermal image on the lower right-hand corner. And then we're comparing that with the Landsat thermal image on the upper right-hand. You can see very good correspondence. We lose some information because the sharpening is based primarily upon the vegetation signature, but you know, it's something that we may have to do if we get down to one Landsat and we start to get into this gap area. And this is clearly not as good as Landsat. Getting down into New Mexico, I just want to point out the New Mexico corridor is very narrow. We've got some ancient water rights from Pueblos, salt cedar invasion. One benefit of MODIS is that we can get fairly frequent looks. So here's a process that we've applied metric to with MODIS in 2007, where we had 26 image dates. And we can see dryness, wetness events as we go from left to right with the dates. So there's a lot of potential in using MODIS, clearly, but we lose that field scale resolution. So I think Martha's going to talk about fusion, Carmelo, some other people will talk about fusion. You know, we've got to put our thinking caps on and make the best of everything. I'm going to skip through these. One of the challenges we have with Landsat is we only get an image every so often, so sometimes they're wet. We have to make some provision and adjustment for that, so we take a wet image and dry it out without changing the transpiration. We only work on the evaporation. Some things we do. Applications in Idaho, let me just say that there's a lot of applications that are based, are open and ready to use ET from satellite-based mapping. Here's a groundwater model where the groundwater modelers are very happy to be able to aggregate actual ET as a big component of the water balance. We can see from left to right that there's a lot of variation in ET from year to year that we can capture from the archive. That's very meaningful to a groundwater modeler. Water planning, if we know what different land uses are transpiring and evaporating, is important. Performance of irrigation projects, if we can take the ET and divide by diversions, we have a pretty clear idea of what the disposition of water is, where that entity might go as far as changing their water management behavior. Various states are branching out now, adapting metric and other competitors. You can read down this list. Each state's got their own needs and applications and their own issues. And water's under tension everywhere, and it'll continue to get more and more. We'll have this poster up. I don't want you to read it, but just appreciate we're trying to tile the whole United States, predominantly in the West where most of the water issues are, but each of these tiles is a fairly important water issue that's being addressed by ET mapping. Just now on the final part, we do have concern, as Jim Irons, Tom Loveland have expressed, about Landsat's future, just keeping enough Landsats in orbit. We've been through this. Funding for Landsat 9 is uncertain as far as when it's going to come and at what pace we can build. Takes about at least 5 years to fund, design, and launch a satellite. So you just don't decide that you're going to have one next Tuesday. Takes some time. How many Landsats would we like to have as a community? We would like to, and as I'll show you, we would like to have a 4-day return time, which probably means 4 Landsats, and we appreciate that that's a tall order. Here's some nice work that Charles Morton and Justin Huntington down at the Desert Research Institute, they're both in the room here. Charles is over there by the wall. They took the MODIS cloud masking archive, went through it, and statistically determined here that if you have one satellite coming every 16 days, like a single Landsat would have, 16 every day turn time, here's the probability of getting a clear pixel for a location every 32 days through the growing season, April through October for here in Idaho. So if I want to produce for 2013 monthly ET from April through October to use in water rights. I want to value every month, and to really follow the evolution of that crop curve, let me just back up. You know, that crop curve is changing. The vegetation evolves. So I would like to have at least 1 point every 30 days to define that curve, right? And the more the better the definition. So here's the likelihood, and I apologize if that's close to the floor with the screen. Here's the probability with one satellite of having a successful year's worth of ET. And you can see for the eastern United States, they're less than 5% chance. So 1 year out of 20, we'd be able to produce a full year's worth of ET estimates, April through October, where we would have confidence in the estimate. Only in Death Valley, where there's no irrigation anyway, you have 70% chance. Okay, now if we go to 2 satellites, which we had with 5 and 7 flying, so 8 days apart, and which we'll have with 7 and 8 flying, hopefully, 8 days apart, the probability does not double, it quadruples. It's an exponential function, okay, largely. So now Southern California is almost 90% chance that any particular year will be successful. We go out into like Southern Idaho here, we're up in about the 2/3, 2 years out of 3, and that's about what we see in the archive. But we get into the Midwest, and we're still 30%. And we've got some water issues in the Midwest we need information on, and we can't get there with 2 satellites as well as we would like to. Okay, so if we go to 3 satellites, it looks a whole lot better. So each one, we try to get about 5-day return time. And then finally, 4 satellites, which is what we'd like to have, and we can get a 4-day return time. Let me just say 4-day return time. You can get that with 4 current Landsats, each 4 days apart, or you could get it with 2 Landsats in the future that happen to have double the field of view. So instead of 160 kilometers, they'd be, say, 300 kilometers in width. And then you can see, you know, a pixel location more often. We could get a 4-day return time. And these dark blue areas are pretty much mapping out where the critical water issues are in the United States. Just forget about Florida. They got too much water anyway. But you look at Nevada, California, Arizona, New Mexico, Colorado, western Nebraska, central Nebraska, Wyoming, central Washington, Klamath Basin. We can nail it with 4-day return time. That's the message I would like. 8 satellites, 2-day return time. It's not going to happen ever, so no need to even look at it, but it's a pretty picture. Landsats 8's coming up. We've talked about that. In your materials, there is this spec sheet that some of us helped Western States Water Council put together. We would like you to read this. This is a very simple message on how to convey the importance of Landsat to the water community. On the back side is something that helps explain to hopefully a wide array of people just why Landsat fits where it fits so well. Why we can't do it with MODIS, you know, a big format satellite, and why we can't do it with unmanned aerial vehicles. Why we can't do it with Rapid-Eye and QuickBird, you know, the 1 meter resolution. There's a real unique need for the 30 to 100 meter resolution of Landsat. So I'd really encourage you to use this. You can pull the PDFs off the web. Just 2 more slides. I'm running late. Where are we going? Probably most of the development groups around the nation, we're getting more and more scripting to maybe help us with automation of the entire process. We'll be running on clouds in the future just for quickness, and to do just much more processing. We'll have to do fusion with larger pixel imagery. However, I do want to caution that there's no substitute for the human intervention and oversight for accuracy and the type of accuracy that we need in water rights. So I hope you don't expect that someday there'll be this big easy button to push and you just order ET images and they just appear out of the blue without any human intervention. I don't ever see that happening for the real serious products. Now, it can produce a lot of good stuff for us, but there's always going to be, unfortunately, the human factor, but that's not a bad thing. We're talking about very valuable water, so it's in my mind, worth the investment. Okay, the two products that we'd like to get from this workshop. One is, at the end of tomorrow, we hope to have kind of a summary, and maybe it'll come after the workshop. But anyway, just to kind of encapsulate where do we need to go with the CT mapping to really fill some of the legal needs, for example. I mean, that's a real critical need that we have. Are we ready to fulfill some of those needs? We'll hear from some of the legal side tomorrow. What kind of accuracy do we need? What kind of coverage should we be asking for to service that need, and what kind of processing techniques? And then finally, the other product that we really need your help on is we need to have a concerted voice, all of us water users, especially from different states beyond Idaho, expressing and communicating the need, like Jim Irons said. You know, it was the Western States Water Council, a unified voice representing a number of states that really communicates to Congress, to the federal agencies, the high value and essence of something like Landsat. So we're going to be working on a very short statement that we'd like to have as an outcome from this workshop, if you don't mind. I probably should ask the federal people that they're free to leave the room when we do this, because I know you guys can't be involved in any lobbying, and you need to protect yourselves from some of this hardball that we have to do to get satellites. But anyway, we need to have a very common, concerted voice. So we hope that you'll be willing to join us in this effort. And then we're hoping also that we can at some point have some future assistance from all of you to be kind of liaisons in your own state, talking to your own congressional delegation, your state engineers, you know, educating them, bringing them up to speed on what's critical, what's the right message to take back to Washington, D.C. to make sure that this happens in the future. It's up to us. If we're the users, we're the ones that have the fire in our belly to know what we need and to ask for it. We can't depend on Washington, D.C. to make those decisions for us, because they're not the users. They don't see the critical need, I think, is with the same intensity and clearness that we users see. So with that, I'll end and appreciate your time and attention. And again, thanks for being here. Thanks.